So now we move on to quaternion quantum field theory, DeMYSTiFiedD. This is actually a book available on Amazon, and my good friend Lowell, who's kind of doing research with me, he said you should read this because it's kind of your style of heavy equations, a few words summarizing what it is, and then the next equation, and then the next equation. And so I was able to read this in about a week or so. I had taken a full graduate year level class in relativistic quantum field theory, so it was like familiar, but it's like, I hope that I don't have to answer all these questions because I'm probably too rusty, but they were all familiar issues for me. And then I went back and said, okay, now if I was to do this with quaternions, how the heck would I do this, and what would my approach be? And it took me 3 weeks to get through 3 pages. I don't feel bad about that because by that time he'd already done the uncertainty principle, he'd done Klein-Gordon, he'd done the Schrodinger equation, he had Dirac. So those are really core equations to quantum field theory, and we're going to show you basically that sort of stuff. So I read slowly, but it was a productive process. And all right, and out of it came what I'm calling the method. If I can just switch over modes. Okay, so new methods really rewrite everything that was done in the past. So special relativity, which applies if things really are moving very quickly, you've got time and space, they're 4 vectors, energy and momentum are 4 vectors, and in quantum mechanics, which applies to things that are really super tiny, you've got the correspondence principles, so you can connect stuff that happened in classical physics to quantum mechanics. You've got these complex amplitudes, you have real observables, sort of stuff. That works if and only if things are really small. And so I was saying to myself, well, let's get rid of those, if and only if sort of situations. Let me just write it once and use it whether things are going fast, whether things are going small. I don't want to rewrite anything, okay? That was my attitude. So the method, as I'm calling it, has just 4 rules to rewrite all equations in field theory. Or maybe I should just say in physics. I probably should just say physics. And nothing is really radical except being this consistent. And we don't really tolerate breaking rules. And not being flexible is actually pretty easy. You just say, well, I didn't do this, so I have to keep on redoing things until it's consistent with my rules. Because nature appears to be this rigid, right? It's like, I'd like to not, deal with gravity today. It's like, no, you will always deal with gravity. Nature will never allow you to take a step outside. So rule number 1 is to keep all 4 vectors together as quaternions. And okay, so examples would be spacetime. Okay, you've got the time element and the space part, and they're together. And for momentum, the energy and momentum together. And differentials. Okay. Turns out that that's a very simple statement to make. There's nothing apparently radical, and believe me, I'm not going to get along with all the books I've recommended. People like think about energy and not concerning themselves with momentum. Or if they do, they'll put it on the other side. That happens all the time. It will be resisted. And in some ways, I think this is, somebody said, I'm not remembering the quote exactly, but it's something about, aren't we lucky that math gets along so well with physics? But is there any tension there? And I would argue, actually, after this kind of talk, that there is some tension. And the tension is that because we're so used to the equal sign, we're so used to saying, I'll put this on the left side, I'll put that on the right side. And do you have any criteria for doing this, making this decision? It's like, criteria, I don't need any criteria, it doesn't matter. Okay? And I think that maybe it does in a certain sense. Because it's a deep lesson of special relativity. People like to focus on energy and ignore momentum. You know, say, oh, well, I'll deal with that if I have to. It's like, no, you have to. Because somebody in a rocket ship is going to look at your equation, and they're going to see the energy part, they are going to see the momentum, and if you don't have it written out explicitly, rocket ship man is lost, okay? So that message from special relativity says, I can't do a calculation that only involves energy. Well, a vast majority of what goes on in these books are calculations that just involve energy. And that little thing bothers me. Okay, rule number 2 is very easy. Drop all factors of I. Factors of I are rather popular in quantum mechanics books, but because I'm using quaternions, it's got an I built in. It also has a J built in. It has a K built in. It's nice to have these things built in. And what I do is I really no longer I stay away from the word imaginary. The word imaginary came about as an insult, right? That was when the people were fighting over whether complex numbers should be used by anybody, okay? And as we know, complex numbers won out, but in the meantime, the people trying to knock them down said, those are imaginary. There's nothing imaginary about space. There's nothing imaginary about momentum. There's nothing imaginary about that kind of spatial derivative, okay? So sometimes language helps. If you step away from language, that was insightful. I should say maybe as a kind of corollary to this, quaternions, some people thought they were really going to be important, and they got into the same kind of super nasty fight. Just quaternions lost. So that's why it's not mentioned in any of your technical books except those that have to deal with 3D spatial rotations, which would be either for rocket scientists or game designers. Those are the only 2 technical books that will have quaternion, an index element to it. Okay, I in fact only had one math book that mentioned quaternions once, and I read that, I know, in 1989, and I came back to it in 1997. So that's the only reason I'm giving this talk today. Is that it was mentioned once, and this is what's come out since that time. Pretty remarkable. All right. So rule number 3: keep all those constants. Write all those factors of C, H, and G. Feynman was actually a big fan of this, and people today say, no, I'm going to use natural units. I don't have to write it out. Okay. So. So that's a kind of difference in attitude. But I think that the constants actually give you a handle on what's going on. Okay, if there's not a factor C in there, well, then you can't be really relativistic. If you've got an H bar, hey, maybe you've got quantum mechanics going on. Quantum gravity, relativistic quantum gravity has a G and an H bar and a C, like the T-shirt has. So rule number 4 is that all equations must be made dimensionless. So this is really, I don't want to deal with the French. That's my whole aim. They've got the kilogram defined in Paris, okay? I love Paris. I love the city. I don't want to go there to find out about the kilogram. So the way you execute this is that you put in only dimensionless things, and they're going to stay that way. Okay? You're still dimensionless. They're still dimensionless. You see, and this is one of these this is actually a little dividing line between physicists and mathematicians. Mathematicians, they're always dealing with dimensionless things. This is a set, and it's got these, collections of numbers. They're always dealing with dimensionless things. That's one of the strengths of the hand they play. So we should copy that if we're coming at it from physics. And it's a nice check on things that are done. Now, I have yet to really commit a different way of saying this is I'm using Planck units. for everything, or dividing by Planck units for everything. So that would be 1 over Planck time. That would be 1 over Planck energy. That would be Planck. Oh yeah, look, that's the inverse. That must be Planck time on the end. Okay, and so you end up writing more and having to look at that wiki page that tells you how to convert all of these units to Planckian units. But so they're the set of rules. The only one I think that's truly a little odd is the thing about using quaternions in the first place. Okay, but once you accept that, then drop in factors of I, keep all the constants, make them all dimensions. That's all we're going to do. So who we're going to subject to this sort of thing? Why not start out with Sir Isaac Newton? He's the one who started all. Okay, so what makes Newton's second law just so darn classical and so darn relevant to our local world? So here is that second law. Nothing's moving fast, nothing's small, nothing's amazing. We've got, father equals mother sort of thing. But I was just wondering, in your own opinion, why do you think that equation is just so important? Do you have kind of a reason why you think it is? All right. It's like, well, it was his second law. He was starting out. It was the thing that kind of told us about inertia, about how you change inertia around. It seems really basic. But can you make it kind of more concrete? I certainly didn't know how until I did this exercise. And that is, I just used the method. And so I've got a time operator acting on mass times velocity, okay? And I made each one individually dimensionless, and I multiply that whole thing, and I think the reason it's so relevant to our world is that there's this zero in every single term. I wasn't taking time derivative and a space derivative. I wasn't dealing with velocity and whatever would go in the front of that. And then I just multiply that out, and I do get the rocket science term out of that, which of course should formally be included, but most people don't do rocket science. And I also think that there's nothing relativistic going on here, because otherwise those zeros wouldn't be there. They would have some value to it. And relativistic quantum field theory, you can recognize the equation with this generator because every value will be filled in. Okay? And if you're dealing with classical quantum mechanics, then one of those terms along the way will either have a constant or a zero. And that's the difference between relativistic quantum field theory, where everybody is really filled in to the max, and classical quantum field theory, which makes, is kind of a step in between Newton and what we've written, a step between relativistic quantum field theory and that Newton equation. Okay, and it turned out that I used this result for my Christmas card this year. Okay, so let me explain my Christmas card. That's an apple falling, and it is gaining twice as much in each kind of subsequent step, as it were. And the math is the acceleration of gravity, g, which is 9.8 meters per second squared, times the square root of g, a small number, h, a small number, divided by c to the 7th, a large number, ends up equaling 4.42 times 10 to the minus 51 as a number, okay? So it represents exactly the same thing. You could say this is 9.8 meters per second squared acceleration, or you could say it's 4.42 times 10 to the minus 51. This bothered me for a full week. I'm so used to my units. Even if I had to go to 32 feet per second squared, I was more comfortable going the English units than going completely without. It's like, then what is it? It's got to be describing the same thing, okay? It's just using different units. Okay, I wipe them out. Okay, but why is it so small? I liked it when it was around 10. I liked it like it. It was okay around 32. Being this small bothered me until I said, hold it. Physics is about my relationship to the cosmos. In the cosmos, I'm sitting on a planet that is stupid joke small. It is nothing compared to the sun. The sun is nothing compared to my galaxy. My galaxy is nothing compared to the whole collection of galaxies that make up the universe. The science has told us over and over again, you are nothing. I'm saying that message again, okay? That's all. I'm being consistent with that message. And that's how I kind of said, I took it a step closer to saying, I guess that's okay. I guess that's kind of cool. And it inspired some poetry, and so I'll read that. And I won't analyze it because analyzing poetry is probably better, like analyzing jokes. So, gravity written without units, tiny beyond the tiniest tiny, gives weight to mountains and butterflies. Even light bends to this game. Lives lived without words, alive, breathing, being and now, give weight to responsibilities and laughter. Even love bows to life. I sent this card, of course, to friends and family. I do send this card out every year to physicists. I'm doing social experiments. This is a social experiment. I don't know how much of what I'm saying is true. I hope it's a lot. I certainly can't be certain within my own shoes that it is. I do outreach through YouTube, through those YouTube videos. This is one of my techniques. I send this card to professors. I actually send it to 5 professors here: Alan Guth, Max Tegmark, Seth Lloyd, Paul Joss, and Peter Fisher. These are all people I have approached personally, and usually at the end of one of their talks, and say, hi, I've got this new idea, and they were polite, they were professional, and they're busy with their own world, and I haven't suckered them in, if you want to say it that way. They are in their own program, they're extremely busy folks. But that's at least one thing that I do to try and get... So these people, they know of me. I am the weird Christmas card guy. And with this body of research, amazingly enough, every year for literally 10 years, no, maybe 15 years, I don't want to think how many years, I've generated a card based on my physics research that certainly was somewhat unique. I mean, it's kind of crazy that this mission started, I think, in April or May. And it's really been wonderful, and I really like the card for 2010. Don't know what'll happen next year. All right. So let's look at the uncertainty principle. Very important. The uncertainty and certainty principles of quantum mechanics arise from the move to operators and the product rule of calculus. This is usually not the way it's explained. I have a hard time seeing things in the standard way. It's because, the uncertainty principle, that gets all the press. That's what they have books and conferences on. That's what everybody talks about. Okay? And there are actually many schools of thought about why the uncertainty principle exists. But here, the way I like to operate, if I can't map it directly to an equation, I'm not happy. Okay? I need my equation sort of thing, my math thing. And it is only momentum in the x direction that is uncertain. Okay? And I actually put a big X through this because it it's a little bit too general, or actually this should be a subscript, but I know this should be a subscript. It's just easier for you to read from back there if I put it like this. Okay, so give me some slack on that. But it really is about momentum in the x direction has this uncertainty. That can be zero. That can be absolutely certain. And everybody who teaches quantum mechanics knows this. Okay, I'm not like, wow, this is a brand new insight. They know this. Okay, they just don't emphasize it. They just say that's the way it is. I mean, that's kind of obvious. There's nothing deep or mysterious about it. But the thing is, for me anyway, is that whatever explanation of uncertainty you decide to settle on, okay, make sure you can explain both the uncertainty principle with it and the certainty principle. You should not emphasize one over the other just because everybody talks about one. You've got to settle on the other. Okay, so the way it works out is that you have these operators that act on a wave function, and one of them is a derivative. In this case, the momentum in the x direction, not a number like x. And yes, if you go on to graduate school, you know you can actually reverse that situation and make momentum a number and position an operator. But either way, one is a number, the other is a bit of calculus. Okay, and this is not the way it's done in standard books because they would have the h bar. But remember my rule number 3. To make this, no, 4. This is rule number 4. To make this dimensionless, gee, I don't have to do much at all. That's nice. I don't have to remember my h bars, square roots of g factors. Okay, so now we're going to look at something called a commutator, which is basically writing these things in both orders. And then they're going to act on this function d. And so when you do that, you use the product rule, and you see that you get that cancellation going on. And so basically, this thing ends up equaling 1. The commutator ends up equaling 1. And if you repeat this exercise with the y momentum operator, then lo and behold, you get 0. So the yx commutator acting on phi equals 0. This, again, is something they do teach you in a quantum mechanics course. And they say, well, I don't know. To me, they're not emphasizing it enough. Because this is purely math. To me, it's totally clear. Or it's pretty darn clear about what's going on. And I don't have to get into philosophy. I just look at my product rule and say, well, in this case, I'm going to end up with 1. In this case, I'm going to end up with 0. But there, you want your h bar in there. And so I'm doing all the calculations dimensionlessly. And, but to me, the key difference between the two is that one ends up at 0 because there is no, product rule kind of thing going on, and one for the other. Okay, so the next time you get into a philosophical argument about the uncertainty principle, which is easy to do, people feel passionate about why the heck it is that way, just ask them about the certainty principle, about why, if I have that position in x and I come in at y. Now, they might say, well, orthogonality, which actually turns out to be the right answer, okay? But it's kind of like, it's almost like they changed the discussion a little bit. And so I like my reason for why there's uncertainty is the same reason for certainty. See? So that to me is being consistent in my logic. And so anyway, that's why I'm on uncertainty and certainty principles.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never over the desk and twirls a pencil.